thank you, sir. Thank you for agreeing to deliver a lecture. Now now the dais is yours. Please.
Yeah. So thank you, Dr. Sweta and Dr. Shyam, for giving me this opportunity to address your audience. And I'll be talking about advanced remote sensing techniques in water resource applications. Though it may find out of context for the theme of this program, like machine learning and deep learning, I have tried to include a lot of examples and case studies where we have worked in the machine learning and deep learning program. So let's go into the presentation. So my presentation outline could be like overview of the water resources, and we'll see just an overview of geospatial technologies, a bit of artificial intelligence. Probably you would have got exposed to this lot many times, and some case studies, and of course in the last I would like to expose you to a lot of earth observations, data and case studies where you can apply this AI or DL or ML applications to derive useful information, which will give you an idea of what are the gaps available in this sort of applications. So this is how we'll be going to. So as you all know, the Earth, almost 96.5% or 97% of the water lies in the ocean, and roughly 1.7% of water only is available for us as fresh water, lying in the lakes, rivers, and streams. And if you can see, almost 0.001% of water is available as vapor, water vapor in the Earth's atmosphere. And ironically, this 0.001% of vapor condenses and falls as rainfall and gives us becomes a major source of fresh water for the terrestrial life in the globe. And another contrary thing is the rainfall that falls on the soil and fills the soil with soil moisture. And this soil moisture, which is also a fraction of the total global water cycle, and this soil moisture helps in growing the crops, plants, and vegetation, and gives life, and it gives us the food. So if you see the water which is available on Earth, only a fraction is really drives the life on Earth. And if you see on the left side of the image, if you see the large water drop is the total available water on Earth, and the smaller drop is the liquid fresh water, which includes the fresh water locked in the ice caps in the polar region. And what is really useful is a small speck that is seen here, that is the fresh water available in the lakes and rivers, which is really useful for us for domestic use and for agriculture and all other purposes. So, it makes us very conscious of that this small fraction of the water is available with us, and it drives the life, and it is very important to preserve this water or conserve this water and use it judiciously. And this brings us to the topic like how to manage this water. So just to give the perspective of how much water do we eat. We drink water, but we also eat water. So whatever we eat consumes a certain amount of water. So for example, on the right side, if you see, if you are eating one banana, or for example, 0.1 kg of apple or a banana, the banana has consumed already 82 liters of water. So they have to irrigate the crop, and if you calculate the amount of water that is consumed to produce one banana, is something like 82 liters. If you are consuming a beef, say a 0.25 kg beef has consumed almost 3,800 liters of water. So this is the sort of consumption of water that we do, and it is estimated like an average Western hemisphere country people for a per day meal, they are consuming almost like 7,000 liters of water. Okay, it may be much lower in India, but so you see, you can imagine 7,000 liters. See, for a normal consumption in India, like over a tank, say a 1,000-liter tank, satisfies a 4-member family for an entire day. For consuming one day's meal, you are consuming almost 7,000 liters of water. The second most important is the footprint of the water. So if you are consuming a pizza and the olive comes from Europe, you are consuming the water from the European countries. So in general, a society to be sustainable, the footprint should be very small. So you should be able to consume things that is around you. But if you are trying to consume things that spread across the globe, that is not really sustainable over a longer period of time. So this gives us a clear picture of how much we are consuming and how far we are consuming this water from. Now, coming to India, the major user of water is agriculture, almost 91%, followed by the domestic use and industrial use. And within agriculture, the water that is used for irrigation, the well irrigation constitutes almost more than 60%, followed by the canal irrigation, and then the tank and other irrigation systems. So in agriculture, in fact, India is not totally irrigated country. Almost 3/4 of the country is rain-fed, and only roughly around 42 million hectares, I guess, is irrigated. And within this irrigated, this is the sort of classification we can arrive at. So we are using more of a groundwater rather using the well water. So this puts us emphasis of what sort of irrigation water management we can do and what are its benefits. So irrigation water management will help us prevent excess water use. It will minimize the pumping cost, and it reduces the soil erosion, reduces the labor cost, and improves the groundwater and downstream surface water. And it also helps in improving the yield of the crop. So this is just to put you in perspective of the importance of water and the water resources in the irrigation water management perspective. Coming to the geospatial technologies, geospatial technologies has 4 major components, namely the Earth observation, the navigation systems, the GIS, and the ICT, that is the information communication technology. Geospatial technology, when we apply, we may use all these 4 in combination, or as a standalone also it is applied, and therefore the business that drives, the geospatial technology, if it has to drive a business, these are the verticals that it has, like geospatial technology, as we discussed, like GPS, GIS, Earth observations, etc. there. And to facilitate these technologies, the facilitators are like open data, the standards for the geospatial data that has been there, and the interconnected systems. This facilitates the use of these technologies, and the processes like business intelligence, digital engineering, and workflow automation. These processes are carried out to derive information, and there are several delivery platforms like enterprise, social media, apps are there, web portals are there. So these are the platforms through which the delivery takes place nowadays to the citizens, businesses, and the government. But to drive nowadays the geospatial technologies, there are several drivers that has come into play. One is the Internet of Things and the artificial intelligence, which is what we are trying to address now. The cloud technology, where one can even if you don't have the resource, you can use someone's cloud to do data storage, computing, and all of the stuff. So cloud is one important driver. The wireless and broadband. The big data technology is also an important driver in the geospatial technologies. So though there are several standalone geospatial technologies. These drivers, I mean, these are very important drivers that enables this technology to bring out a lot of information quickly through automation and in a useful manner. So basically, just to tell about the artificial intelligence, you must have already been seen these things. Artificial intelligence, as per definition, is the science and engineering of making intelligent machines, especially the intelligent computer programs. So artificial intelligence basically tries to make machines which think like human beings. So we are trying to replicate the nature of human brain onto a machine, and these are achieved through machine learning, like deep learning, predictive analysis, the natural language processing programs like classification, translation, and data extraction, expert systems, planning and optimization, robotics, and these are several gamuts of or branches. We are like we would like to replicate the thinking of brain into a machine. So we are trying to use this sort of technologies in the remote sensing area to derive information much more accurately and much faster. So artificial intelligence, there are several methods you must have seen. The machine learning, which uses the statistical methods. The deep learning uses the neural networks, maybe artificial neural network or CNN, etc. The big so it works with the probability concept, and the genetic algorithm uses or taps the heuristic approach modeled after the natural selection. So these are broad classifications or methods of artificial intelligence. So before getting into the actual aspects of the applications that we would like to discuss, I would like to just throw some light on this DIKW pyramid, which is the knowledge management cognitive pyramid, it is called. The bottom of the pyramid is the data. So data as such are plentiful. They're all around us. And data as such is not a useful product. So one has to analyze and bring out information from these products. So data with your context in which the data has been generated and used. So adding the context for the data and deriving the information is very, very important. So once the information is derived, it becomes a little bit useful. But if you add some experience to the information based on the ground truth knowledge you have or the local knowledge you have, based on your experience, if you can derive information or derive inferences from these information, then it becomes a knowledge. So so you go up the pyramid with the knowledge, where knowledge depends on the individual's experience, and with this experience he relates these informations and tries to derive information. I mean, try to derive the knowledge. And knowledge, when it associates, because each individual have a different experience, and therefore the information comes out of it will be different. And therefore, if one chooses the right consequences, if he applies those knowledge and it becomes really a good consequence or a good positive consequence or positive feedback, then it becomes a wisdom. So here is where we generally stop, that we stop with the knowledge, and all the great people who use this knowledge with their wisdom, means with their good experience, and then try to predict things, and then try to forecast things, and therefore they are called wise people, and therefore that's how. So the things that is below the knowledge is all already there, already happened, and what is that those things that happens beyond knowledge or the wisdom is all futuristic. So that's how this pyramid is explained. And the risk of decision taking in the pyramid is that if you take a decision using just the data, the risk is very high. And if one takes a decision at a wisdom level, the risk is very low. So that's how. So the same concept applies in your artificial intelligence or machine learning or deep learning sort of a thing, where the system analyzes the data and gets some information. And once the information is there, it gets trained with the ground truth information and gets the knowledge. And then based on the knowledge, it starts to sort of predict things, and then it tries to predict the future or forecast things in the future. And that's how the artificial intelligence also resembles this sort of, it is popularly called DIKW pyramid. So let's get into some case studies. Like, so the role of artificial intelligence in the irrigation management. Like irrigation is a space where you have several applications for artificial intelligence to solve the near real world problems. The key is or the key to realize this potential is the data. So you should have a lot of data to analyze these issues of irrigation management. So this is the first case study I would just like to discuss. So if there is a farm, so how an artificial intelligence can help increase the crop production. So nowadays, so for growing a crop, and each crop, say for example, a tomato crop, and each crop or each variety of a crop will have the maximum potential yield. Okay, so the output, if all the conditions are favorable, the tomato can yield a certain X amount of fruits, and the farmer tries to strive to achieve this maximum yield in his farm. The right way is to provide all the inputs that it requires, like in a field, he would like to give the maximum amount of irrigation, maximum amount of nutrients, and all other things. But if you are giving the maximum amount of all the inputs, then it may cost him a lot. And therefore, the way he has to, if he has to gain profit, or if he has to profit from the cultivation, he has to actually reduce the cost because your output is fixed. And unless you reduce the cost, you will not be able to achieve your maximum profit. So in order to reduce the cost, you have to reduce or optimize the inputs that you are going to provide to the crops. So there are several variables in a field. If you, for example, if you take example of applying a fertilizer, if you have a soil map which gives the fertility of the field spatially, there are certain pockets of the field which are inherently very fertile, and certain pockets which are inherently very less fertile. Now, under conventional systems, you apply uniform dosage of fertilizer throughout the field. But in a precision farming sort of a system, you optimize. So you apply less fertilizer for a highly fertile soil, and a high fertilizer dose for a less fertile soil. And therefore, you are trying to reduce the amount of fertilizer application. Similarly, if you see the irrigation, you have sensors across the field nowadays, and you have also satellite-based inputs or drone-based inputs coming in, and you can actually spatially vary the application of irrigation through a drip system or a controlled system. And if you are spraying again, so you can apply fertilizer to the pockets of a field where actually the infestation is more, pest infestation is more, and the remaining places you can just avoid spraying. So this way, when you're optimizing the inputs by the use of precision agriculture or an artificial intelligence system, you are trying to reduce the cost, and therefore you are maximizing your profit. So this helps in creating an optimal irrigation scheduling and distribution. You can also have systems which identifies the problem in your irrigation systems or any other mechanisms or say input mechanisms that is there in place, and it also helps in maximizing your profit. Now, this is a schematic diagram or architecture of a IoT-based irrigation system using open source technology. The middle vertical that is shown here is the server data processing and intelligence layer, where you have a web service program which accesses the weather data both from online, and if you have your own weather systems, it can access also those weather informations. And you have a centralized database. Centralized database may contain your fertility information of your soil depth, the water holding capacity of the soil, and all such informations can be there in your centralized database. Your crop information will be there. What is the response of the crop for different types of soil, moisture deficit can be there. So all this can be there in your centralized database. And the application planning can happen here. And here you have a web service which controls the motor through a hardware, the Raspberry Pi, and you have access. You have sensors. If you have sensors across the field, and these sensors can be accessed by the web service or field sensors, which will be used as an input to predict the soil moisture, and therefore this will help you in activating the irrigation system. If the soil moisture is less than the management allowable deficit, it can trigger the irrigation to apply irrigation in the field. Similar to other aspects as well. Here again, you can have forecasting of the things, like if you take the weather forecast information here, and if there is a rainfall that has been forecasted in a day or two, and if the soil moisture is just right to hold up to that time, you can avoid irrigation. Thereby you can minimize the amount of water that has been applied, the power supply that is used to irrigate. So a lot of cost saving can be there. So this sort of smart irrigation systems are presently being used in countries like Israel and US. There are a few places in India also they use these things. The only problem here is we are having a very small holdings of farmlands, which doesn't make it feasible for this sort of application. And therefore, a large corporate or large farmers can really use this sort of expert system or smart irrigation systems to their benefit. Now, the data source for artificial intelligence are many. One of the main source of data is the geospatial technology, or the remote sensing data, or the earth observation data. There are a lot of in situ observations are also required, because many of the data cannot solely come from geospatial data. So a lot of informations from the ground has to come. So we may have to install sensors, IoT-based sensors and other sensors. There are SCADA systems that provides you data, and then there are crowdsourcing. The people can carry a mobile app, and then they can provide you information as well. So these are all the sources that the artificial intelligence can use. Now we'll get into some of the AI/ML based studies that NRSC has carried out in the field of urban studies and agriculture and horticultural areas. So one of the studies on the inventory of coconut plantation using Cartosat imagery. This is a feasibility study. Then trees outside forest, another important study which led us to getting a project for assessing the agroforestry resources using geospatial technology from Food and Agriculture Organization. And With the Delhi Development Authority, we did a project for change detection in the built-up area and the vacant lands. And also we use the UAV data also to do some classifications. This is the overall methodology that has been adapted in the deep learning. So we use the high resolution data, okay, and then we do the pre-processing, basically the geometric fidelity and the radiometric fidelity, and then we do a classification or the training chips we do using manual or object-based image analysis, and then label the samples, and then this is inputted into the DL model, and then the parameter optimization happens, and then training and testing. And then the trained model provides the output, which then is tested for its accuracy and inferences are made. So this is the overall framework of the DL model that has been carried out at NRSC. The image chips that they used are 512 by 512 raster tiles. They use for training and validation. For training, they use 80% of the data which is collected in the ground truth, and 20% of the data they use for validation. And in the first stage they use the 256 by 256 tiles, and then once it doesn't satisfy the conditions, analyzing the training loss and validation loss and accuracy, they increase the size to 512 by 512. And all this tests goes through like high training error, high validation error, and all these models using the satellite data. Finally, this model is used on the entire area of the satellite data to give the classified outputs. So this is the overall methodology that has been adapted probably in most of our studies using deep learning. This is the sort of distribution of ground truth. Actually, this is an area where we have not much is there. For each district, we have used almost like 400 to 800 training sites. And this is the sort of 256 by 256 chips that we generate for training. And we classify these chips for what we are looking for. Here we are looking for the trees, tree plantations, horticulture, trees outside forest, etc. So in this first chip, you can see this is a cropland. So so this is a cropland. So it is skipped, and the northern part here, the brown area is the horticulture crop, and therefore it has been marked. And this small patches are individual trees. Here again, in the second chip, you can see these are all the cropped areas, and this is the road, and along the road there are trees, and these trees are classified here. So each required class is coded as 1, 2, 3, and these are the classes that are forms the basic input chips for the ML program. So you can see this sort of see here. Here you can see a water tank here, and the trees around the tank has been considered, and along the road has been considered, and these are the shrubs there with trees that has been considered, but not the cropland here. And this is again a horticultural field here. So this sort of classification is being carried out. This is done manually through visual interpretation or using an object-oriented approach using e-cognition software or other softwares. Now, this is one study of inventory and monitoring of vacant sites for Delhi Development Authority. As you know, in places like our metropolitan cities like Delhi or Bangalore or Hyderabad, there is a lot of demand for vacant space, and the vacant space that belongs to the government slowly gets encroached, not only by the poor people, but also by the known cartels who try to encroach on these lands. These vacant lands can be places like parks, land reserved. It becomes very difficult for the authorities to vacate them. If they go to court, it takes years to vacate them. So Delhi Development Authority want to monitor these vacant lands in their jurisdictions, and have a close watch on that. So the background is the developed automatic detection, change detection using the temporal very high resolution remote sensing data. The data we used here are Cartosat 213, ComSats, QuickBird, TripleSat, and Iconos. And so the model is also developed so that it accommodates all these sensors. So it's a multi-sensor deep learning model for extraction of the building footprints, including built-up area, parking lots, roads, water, barren, and other areas. Almost 1,800 training samples were used to train the model and validate. The accuracy we achieved something like 87%. And GUI, a graphic user interface, is also developed in this project to facilitate the authorities to use them. So this is a sort of multi-class training samples that we have generated for building roads and open lands. These are the training samples that we have collected. So this image shows here like how the prediction versus ground truth. So this is the satellite image, and this is the ground truth where we visually manually have encoded them as a chip sample. And after validation, how the model has predicted this pattern here is shown here. We can see more or less similar patch or matches the ground truth information. So the model has performed well here. On the right side, it's a case study on the automatic detection, change detection of the image of a same place in 2 different time periods, where you can say T2 in 2017, you can see there are a lot of construction has happened and built-up areas come, and you can see the model has able to predict this thing. Sir. Sir, నేను ఒక లెక్చర్లో ఉన్నా ఆయనకు 1 hour పడుతుంది. అచ్చా అచ్చా నేను వచ్చేస్తాను. So you can see the changes that has been captured here, and this clearly gives the changed scenario, and therefore if this is an unauthorized construction, the authorities can actually start taking action. But if it is done frequently, you can even capture these things when it is under construction itself. Now, this is another example of change detection using deep learning method. Semantic segmentation based building footprint extraction has been done for 2 areas. These are basically layout, a housing layout, where you can see in T1 it was the houses were sparsely populated, and the T2 time the area must have developed and a lot of houses has come. So the classification image, the building footprints are extracted for the 2 periods. You can see the classification that has happened exactly to the buildings that has been present in both the images, and the difference image is shown in the right side, where you can see all these green lines where the new buildings have come up. This is with reference to the T1 image that has come. So you can easily find out which are all the plots that are where the new buildings have come, and accordingly you can take a call. Now, another study is about the coconut plantation. This is a feasibility study which was done very initially, just to try out how the deep learning technique works over agriculture area. The problem is when the geospatial data, especially the Earth observation data, increases in its spatial resolution, there are a lot more details that is coming out. Okay, so in a coarse resolution data, yeah, coconut field will be covered uniformly in 2 or 3 pixels, and they have a uniform or average tone. But when you go into a high resolution data, which is a sub-meter resolution, you have a lot more details that is coming out. You have a tree crown it is seen, the background soil is seen, the tree shadow is seen, the vegetation that is underneath the tree is seen. So there are several other things that is coming out. And the normal classifiers or a per pixel classifier will give you so many classes, you really end up in a mess. So it is really not feasible. To some extent, the object-based classifier does better, but when we deployed this DL-based method, it is much more. It gives a much more better result. So the classification of high-resolution data ends up, because of the large heterogeneity, has a lot of inherent problems in classifying in the conventional method. So here, DL method was adapted for the inventory of coconut plantations using the Cartosat-2 images, where we used a unit architecture. This part of the study area is from Tumkuru district of Karnataka, where you can see these architectures were adapted, were tried out, and you can see the accuracy with which each model has given us the result. These are the results of individual models, like the hybrid Siamese, then the custom unit, and then mobile net, etc. And you can clearly see the boundaries have been clearly demarcating the coconut plantations alone. Very nicely it has come. And this actually encouraged us to expand our area of study and application of deep learning into other areas actually. So we then proposed a project with the Bangalore municipality in order to find out the greenery within the city of Bangalore city. So we want to find out the trees outside the forest within the Bangalore city. So that was a sort of proposal we made, and it was approved. And the objective was to develop a methodology for inventory of trees outside forest in the urban landscape using high resolution data and deep learning. So with this study, we started out the work, and then we collected a lot of ground truth. So this is the ground truth that has been collected from the Bangalore city. Using grids, we collected samples, and using these samples, we created the chips, like labeled the training samples here, and then we applied over a lot of different scenarios were there in the cities. Like there were parks in which the trees were there. There were roads, avenue trees were there. There are lakes in which the weeds and the trees around the lakes were there. There are reserve forests within Bangalore city. There are some forest plantations. So forest department, does plantation job, and those things are there. Some mango orchards are there. So there are different scenarios within the city. So all these different variables or varieties were brought into the training samples, and this is the sort of result we got. We got an accuracy. Here you can see we got an accuracy of almost 88% when compared to the object-based image analysis. You can see here in this image where this is a golf course, where you can clearly see only the forested or the tree areas has been demarcated, and all the background grass is left out. So this is the sort of advantages we got. Then secondly, when output is thrown out by the DL method, we will not directly generate it as an output and provide it to the user. We do a lot of, we cross-check it for quality, and then we do some manual editing because certain artifacts will be there. And this method actually it reduces those artifacts. I mean, and then in turn it reduces the time taken by the for the manual editing as well. So this gave us a very good result, and this was highly appreciated by the Bangalore authorities, municipal authorities. Excuse me. So here the trees are available in small patches in the urban area, and here there are trees outside forest in a linear pattern, probably along the roads in a housing layout. And these are trees as a large patch or a shrubland, and this is in a golf course. So yeah, all these classes are nicely delineated. So these are the patterns that the CNN classification has given out. So you can see nicely the linear patterns or the curvilinear patterns of the natural vegetation trees have been marked out. This is just to show you in a close-up how it works. So based on the result of our Bangalore experience, we wanted to assess the agroforestry or the trees outside the forest as agroforestry using a very high spatial resolution data. Actually, at that time, the Food and Agriculture Organization was looking out for such a information for the country. So as a pilot study, we proposed to develop an application of using geospatial technology for mapping agroforestry using high resolution satellite data and using machine learning techniques. So this was our study, and 6 districts were chosen across the country having different agro ecosystems. Okay. So it extended from like in Karnataka, it was Dharwad and Hassan. Sita. Okay, based on the experience, our previous experience with the trees outside forest within the Bangalore city, we proposed a project to estimate the agroforestry using very high spatial resolution data for Food and Agriculture Organization, which was actually looking for this information, for the country. They were also want to estimate the agroforestry, because agroforestry is a very, very important resource. It's an additional source of income for the farmers. So whenever there is a drought or some other issue, they will use these trees and the products from these trees to have a living. So this information was looked after, and we proposed a project to derive agroforestry map using high resolution spatial data and also using a machine learning technique. And then here we tried to, we worked on 6 districts which are distributed across the country in different agroecological zones. In Karnataka, we worked on Dharwad and Hassan, UP Sitapur, Yamunanagar in Haryana, and Bilara, Rajasthan, and Johat in Assam. All these 6 districts are distributed, and then they represent different agroecological zones. And we used high resolution spatial data like 0.6 meter merged Cartosat band data and CompSat data of 0.7 meter resolution. And here we basically concentrated the major plantations. Plantations includes mango, coconut, coffee, tea, all the orchards as a plantation, major plantations. And then the forest plantations are also included here. And other trees outside forest, which includes the trees along the avenue, along the roads, and individual trees in the farmlands. So these are the sort of major classes we were targeting. So basically, using the deep learning technique, we derived these informations. On the other hand, we also used the LULC map, 1:10,000 scale map. And then we have already major classes or cropland classes here. So we try to match these things, and if it is in agreement, then we derived a agroforestry map. So here I would like to emphasize that you can see that the validation accuracy in all these districts was far beyond 90%. And this study was highly appreciated by the FAO. So these are the different scenarios that we encounter in trees outside forest. Like this is a nalla actually, and this you can see trees along the nallas here, and there are individual trees that is in the distributed on the fields. This is another river where there is a small patch of forest-like vegetation here. There are different scenarios, like this is another pattern here, and this is an urban area where you can see the vegetation or the trees within the settlements. So you have to classify this. There are horticulture crops here, there are forest plantations here, there are again here there are small horticulture crops may have trees of different ages, like some plantations may be very young, so you have a larger soil background. You have a matured forest horticulture plantation where the canopy is covering the entire soil. So there are different types of horticulture plantations depending on the age. There are trees scattered across the farmland like this. There will be uniform farmland, but the trees will be scattered. So these are the different scenarios that the DL tries to capture based on our training. So this is the challenge actually, and I should tell you that DL really performs well, and for this sort of scenario and high resolution data. This is the same study which I have just told about. Here you can see the major classes that we have derived here. And this is another classic case study where we did the ML for a larger area. So on the top left, you can see an area which has croplands. You have an urban area, and you have rivers here. Okay, so there are all sort of things there. And when we applied the model for the entire scene, you can see the results on the right. You can see vegetation in a linear pattern along the drainage. Okay, so this is a drainage, or you can see a small nalla or a river, where along the river there are a lot of plantations. You can see how nicely the DL has classified these vegetations, as well as the plantations, I mean trees outside the forest also. And this is a area where urban area where the settlement and the trees along the roads are inside the homes are nicely classified. And this is the farmland, flat farmland, where you can see scattered trees are there, and it has been nicely captured, as well as the trees along the roads. So now the Earth observation is now maturing, and then now we have a lot of data from unmanned aerial vehicles also. So the major challenge with the UAVs are that it provides data much more high resolution than the satellite data, in the order of few centimeters. So recently we had a UAV flight, and those images were provided to us, and we deployed a DL method to derive the here basically we want to derive the coconut crop details. So you can here I would like to highlight here in this bottom left, you can see this is a coconut plantation, and you can see different class, like you have a coconut tree crown here, and the shadow beneath there, and the open barren land surrounding these trees. So this is the sort of image you get. And here you can see the same coconut plantation, but there are some crops that is grown in between also. So when you try to classify using a conventional method, per pixel method, this will come as one class, and the crop in between will come as one class, and then the soil will come as a one class, and you will really face problem in aggregating these things and classifying it as a coconut grow or whatever it is. If you adapt a majority class, here you will get only a barren land sort of a scenario. So such complications are there, and here the DL plays a very, very nice role of extracting the information and putting it the required output, like because we are providing it the training samples and labeling it as a coconut grove. So that is a major advantage we have here. The use of UAV, here the objective was to use the UAV data to map multiple cropping systems and develop and a development of OBI, means object-based image analysis, and DL technique for climate. So we compared these two things. And here the resolution of the image was 5 centimeters, and we have 5 bands here. The multispectral band is about 15 centimeters. It is again part of Tumkur districts. So here the same methodologies have been followed, and you got the classified output here. And this is a similar study with UAV for different types of segments. Like this is for the coconut plantations on the left. So you can see nicely the coconut plantation, and within the coconut plantation also you can see the other trees, like arecanut trees are there along the within the coconut groves. And so, and this is a arecanut plantation here. So you can even classify within the field also the different types of crops that is coming out very nicely here. You can see yellow is a coconut grove, and the green patches are the arecanut plants. And here this is a building area or a settlement area where you can see the built-up area is also nicely come, and the individual tree crowns are also nicely mapped here. And you can see within the tree crowns also, you can see different types of trees coming out. Like these black and these green crowns are basically belonging to the coconut. These are coconut trees, and these brown crowns are other trees. So you can see within these trees also, you can have different types of classes that are coming out. So this is really, really amazing actually. Which is quite literally not possible in the other types of classifications. And this is a building urban area. Here again you can see the other trees, the garden trees here represented in brown color, and then the coconut trees coming out as a green color, and then all the built-up area in cyan color that is coming out very nicely. So this clearly demonstrates the advantage of a deep learning method in classifying the satellite data very nicely. So in NRSC, we are involved into various, in water resource group, we are involved into various operational products. One such product is the estimation of evapotranspiration for the entire country. So we are estimating the evapotranspiration using the NPP SOMI data. NPP SOMI data is basically the thermal data is around 750 meters. So we are trying to derive the ET for the entire country at a 750 meter resolution. But 750 meter resolution, 750 meter resolution evaporation product can be used practically, operationally, maybe at a project level, irrigation project level. But the need of the hour is irrigation scheduling at farm level. Okay, so if you can get a evapotranspiration product in every field, so it gives you the information of how much the water is consumed in each field, and therefore you can even or how much the crop is stressed within the field. So based on which you can take a call on whether to irrigate or not, whether how to do irrigation scheduling or not. So we are in the process of downscaling this ET product. So what we did was we try to downscale the ET product of a 750 meter resolution to say something like 30 meter resolution, which matches the Landsat data. So we adapted a machine learning technique and an artificial neural network technique. In the machine learning technique, we try to use on a single day, on a matching day, say both the core resolution and fine resolutions are available. So the AET fine resolution is a function of AET coarse resolution and two other co-varying parameters like the NDVI and the LST. Finer resolution, and this finer resolution is carried for the next days where the core resolution is available, AET is available, and try to downscale those things. So we did the downscaling, something like this, and we also used artificial neural network to do the downscaling of AET. And this is the sort of output we got from. So this is the fine resolution Landsat based NDVI. This is LST, and this is the derived output, AET output from the fine resolution. And this is the core resolution. This is actually a 5.5 kilometer resolution AET output here for 2 days. I mean, so we used this function to derive an output of fine resolution using regression technique and an ANN technique. So it was really, I mean, comparable with the actual results. So you can also do a downscaling using ANN and deep learning. So these are the statistical results of the various techniques we have adapted here, where we can see the artificial neural network, nonlinear regression, co-grinding, distance, subtraction, disaggregation, regression, disaggregation. And we found that the overall ranking, regression disaggregation was giving a better performance, and co-grinding was giving the second best performance, and distrand is another methodology that gives a thing, and fourth was the ANN. So this is the sort of thing. This study is still going on. It is not final. We are still trying to do the thing. This is in the starting phase only. Now, having described all these case studies, now I would like to focus on our water source sector, where I'll tell you several works that we have carried out, and there will be several gap areas will be there with which so you can try to address those gap areas using DL or ANN techniques. Basically, this is to give you an understanding. You need not actually follow the same studies, or you will encounter much more better or more complex studies for which you can adapt the DL and ANN. So this is basically about sustainable development. You'll be knowing. Okay, Earth observation system has 4 major components. One is the Earth data acquisition. Before Earth data acquisition, there are different Earth observation platforms like geostationary platforms, low Earth orbit platforms, aerial platforms, and UAV. UAV is the latest one, and it is becoming more and more popular for any local applications. And aerial, of course, you require an aircraft, and it becomes more costly. And low Earth and geostationary is also a very, very important observation. So, so in the Earth observation system, you have a data acquisition. So from the satellite, you acquire the data. So in the ground segment, you have antenna systems, etc. You acquire and then process the data, and then the processed data you provide. You do it using a data processing system. Data processing systems are there. So you do all the basic corrections, both radiometric and geometric, and then you try to disseminate to the users. Yeah, and there, using this data, we derive a lot of products and services, and then we try to disseminate to the users. And there are several applications that is built on these products and services and the satellite remote sensing data. So this is just to give you a broad overview of the Earth observation systems that is available. So in the enabling techniques, you have a lot of customized software, model outputs, visualization using several image processing softwares, etc. And the main users are the public in general, governments, researchers, academia, private industries, and international users. Then institutionalization happens at ministry, department, and other institutional level. Okay. Now, in water resources, what are the geospatial applications? This gives a list of geospatial applications in water resources. It is elaborate, but not though exhaustive. You may find many other applications not listed here. So there are snow melt runoff forecasting, inventory of glacier lakes, monitoring of glacier lakes, flood hazard zone mappings, etc., etc. There are surface water logging is there, salinity mapping is there, etc. And here again you have some more list where you can have assessment of reservoir sedimentation. So there are several applications that are available where geospatial technology is used in the water resources. Now I will just explain you a few of these cases where Earth observations can be used, and you can also use the DL, ML, or artificial intelligence AI techniques to do this work. Here, this is a image where this is a part of a irrigation command area where there's a program called AIBP, Accelerated Irrigation Development Program, sponsored by the Government of India, where what is that? I'll come another 15 minutes. Where you have to where they fund the projects for creating infrastructures like canals, branch canals, and up to distributaries and field channels. Okay, so but in many places the irrigation projects are complete, but they are not operational. So they, on paper, they say the potential has been achieved because all the canal networks have been completed. But in reality, there are a lot of gaps. So you can see on the right image, there are canal that is laid out here, and there's a small gap here. And again, the canal network is laid from there around. So these gaps are basically maybe a problem due to land acquisition or some litigation or several other local issues may be there, where the authorities could not construct the irrigation canal here. So on paper, you have 99% of the canal completed, but this 1% is crucial because without which the canal water cannot reach the tail reach. So, so this sort of application can easily be addressed by DL and ML. And this is another example of monitoring the cropped area within a project, where this is a project called Jurala project in Telangana, where the ABP was implemented, and during 2005, you can see the cropped area that is there during till 2005. Though the rainfall is more or less the same throughout this study area, throughout the study period. You can say after the AIBP was implemented, the irrigation area has improved drastically, and it is consistently above around 20,000 hectares. So this is one classic example of monitoring the command area over a longer period of time and how the cropped area has increased from the initial stage. And this is some sort of a near real-time inputs that Earth observation gives. This is a part of the Hirakud command area, where this is the Hirakud reservoir, and this is the command area before irrigation. This is on 19th December. In 3rd January, the irrigation has started, where you can see the blue tone are the irrigated fields. Basically, they grow paddy area, so there are a lot of puddled fields will be there, and therefore the water. And the irrigated area slowly starts increasing. So you can see the chronology or the transition of irrigation and the development of crop through the command area in Hirakud command. So where you can see the cropped area increases first in the head reach because of the irrigation that it received early, and then slowly it gets to the tail reach. And you can also see the different tones which represents the health of the vegetation or the type of the crop, where you can see the head reach is much more greener than the tail reach. So it is so the head reach is mostly early zone, and tail reach is mostly late zone. This sort of transition and near real-time input for reservoir operations can also be provided. This is another example of Narayanpur project, where this entire project has been developed in the SWOT model, where you have all the informations like soil, canal networks, the evapotranspiration, everything, all the water component, water cycle components are estimated. And as I said earlier, once you know the amount of water that has been transpired or used, and the soil moisture, where you can find the deficit in soil moisture, you can actually advise the authorities to release water or irrigate the command area. So this sort of applications can also use a lot of artificial intelligence to automate these systems. Though these are large projects where a big organization is running behind it, running the day-to-day affairs. But these are the applications that an artificial intelligence or a smart irrigation system can really put to use. And this is another application where we monitor the water spread area of the water bodies across the country. All the water bodies beyond 2.5 hectares are mapped at every 15 days interval. This is the water spread area is one of the important essential climate variable across the globe, and this gives a lot of information of the water resources of a place. It also gives the seasonality of the water body, whether it is a perennial water body or it lasts 1 season or 2 seasons, based on which some informed decision can be taken on how much area to be irrigated. And secondly, it can be additionally used for raising fishes for aquaculture. So if it is a short duration water body, then type of fish will vary, and if it is a biseasonal water body, the type of fish grown can be different, and therefore it gives a very important to the fisheries department also for the type of fish they want to grow in these water bodies or release in these water bodies. So this is available in our Bhuvan web portal also. This is another application where reservoir capacity estimation can be calculated periodically. The manual estimation of reservoir capacity is quite costly, laborious, time consuming, whereas you can use the earth observation data to estimate the reservoir capacity frequently using this sort of temporal changes in the water spread area. So for each level, and the respective water spread area is estimated, and water spread area elevation curve is drawn, and the elevation capacity curve will already be there for each water reservoirs. And using this information, you can actually recalibrate the elevation capacity curve of the reservoir, and therefore you can estimate the reduction in the capacity of the reservoir. This is another example of this is another project we carry out in the Himalayan region, where every year we estimate the snow melt runoff and forecast the runoff to the project authorities in the northern part of the country, especially the Bakra project, Pong Reservoir, where these models estimates the flow in the Sutlej basin into these reservoirs. This model is run during the summer months, right from January up to April, May, where the snow starts melting, and these are the basic inputs that goes into the model, like insulation, snow albedo, land cover, LST, and snow cover. And the model provides the discharge that is expected to arrive on a daily basis. And in the Himalayas, there are a lot of glaciers available, and these glaciers melt at its mouth or snout, and then they flow into the river. But at some point of time, or occasionally, what happens? The river that is flowing downstream gets blocked due to some landslides. And this has to be monitored. So we monitor these glacial lakes continuously, both for its size and the increase in the water spread area. Because if these lakes increase in size and volume, it is a potential threat for the authorities or the settlements downstream, and therefore it has to be monitored thoroughly, and the probable discharge from these water bodies are estimated and provided in a hydrograph, and this will help the authorities to safely release the water through appropriate means. So this is one study, and the runoff model also is we do inundation modeling also. If there's a dam burst and what is the sort of inundation that happens downstream, that is also being carried out. And as you know, as I said in my earlier slides, majority of the irrigation in India is done through wells. And this is one slide which shows the different scenarios where there is a tank command here. And within the tank command, you can see a lot of open wells there. Basically, these tanks are basically meant to inundate the water, but it also acts as a recharge point for these wells downstream. And nowadays in Tamil Nadu, this is being, they don't even operate the sluice. They even shut the sluice and then keep it very intact. But due to the percolation or the seepage from the tank, recharges these wells, and they start irrigating from these wells, and they can do irrigation for 2 to 3 seasons. This is another information system that we developed for Telangana called TWRIS, Telangana Water Resource Information System. You can go online and check, and it gives all the information. So the fundamental for your modeling and all these techniques is the data. This is one such platform. We have all the data for water resources for Telangana. About all the major medium reservoir projects, the tanks, including the name of the mandals, every detail is available. Almost 45,000 tanks are geotagged. The hydromet data, daily AWS data, everything is available. You can just have a look. And this is what is okay. This I'll skip. Okay, now this way forward, there's a lot of scope for the use of AI ML for decision making in agriculture and water resources. It helps in the development of many decision support systems for many of our problems or the issues that we face. Anyway, that's it. Thank you very much for giving me this opportunity.
Hello, thank you so much, sir. Thank you for a very informative lecture.
Yeah.
This lecture covered wide applications of Earth observation satellites, geospatial technologies, artificial intelligence for effective and sustainable management of water resources, irrigation water management, urban development monitoring, agroforestry monitoring, and also you also briefed about smart irrigation management and also deep learning methodology. Thank you so much, sir, for covering so wide applications of remote sensing.